been here on Tuesday. Otherwise, I could have learned a lot from Michel Brun's talk, where I bet he showed all the beautiful results from Paris. Okay, so this project has a name, and it's a Circus. So it's a circular Rydberg atom quantum simulator, and the architecture we want to work with, I think I don't have to convince anybody here, is tweezer arrays that are really flexible in terms of their tunability in geometry, in qubit number, dimensionality. And this is my reduced slide of what Christian has shown us. So I have only two groups here, which I think are the kind of ones that pioneered this architecture. And so I would like to, in this project, combine this now with the control over circular Rydberg atoms that interact on these tweezer arrays with the main prospect to increase the coherence time of this platform, and then use it for the various applications that we are all aware of, mainly in the context of an analog type quantum simulator. But if the control of these circular Rydberg atoms kind of improve and develop, I think there is also a playground to think about using them as a new qubit, as kind of alternative qubit for a gate-based approach. Okay, so maybe to remind you briefly of what circular Rydberg atoms are and why they are useful in this context, let me remind you of the way that Rydberg states are typically used on this tweezer platform by actually doing excitations via optical photons to low L Rydberg states, which may be an S state, P state, or D state, and then encode a spin or a qubit in the atomic ground state and the Rydberg state. And we all know that these states, they can be nicely optically accessed, but for the same reason, they tend to decay back to the ground state. And this limits the coherence time of this platform to typically tens of microseconds. So a way to actually switch off this optical decay is to increase the angular momentum of the Rydberg electron. And if you do that to the maximally allowed number by quantum mechanics, then you end up in a state that has an angular momentum n-1 for a given principal quantum number n and magnetic quantum number ml equals L. And that is the circular state. And this state, simply due to selection rules, cannot decay back to the ground state by emitting optical photons. So that gives these states a very long lifetime. And what we want to achieve in this project are lifetimes that are on the order of tens of milliseconds, which would improve this coherence time by 3 orders of magnitude. The qubit or the spin system that you would implement then in using these circular states would actually also be controlled differently to this optical kind of qubit. One could encode, for example, a spin in neighboring circular states and connect this via microwave to get control over the qubit or the spin. As I said, I really regret not to have been here on Tuesday. Otherwise, I could have learned a lot about the new results from Paris in Michel Brun's talk that have been setting up experiments where they trap rubidium atoms in tweezer arrays and have now shown this very beautiful control on the tweezer platform of the circular states in a cryogenic environment where they showed lifetimes that are on the order of milliseconds now. The project that we are heading for is we'll use strontium atoms, and on the next slide I will discuss a few of the benefits that come with this atom. And we are working on a setup that is supposed to operate at room temperature without a cryostat. The idea to gain this long lifetime then needs some additional work to be done compared to a setup that would maybe run at low L. And so for this, one has to remember that this optical decay of the circular state is certainly forbidden by selection rules, but blackbody radiation is really detrimental for these states. And so they tend to couple to neighboring manifolds, hydrogenic manifolds, by microwave photons, and in a room temperature kind of environment, without doing nothing to this state, it would decay on the same time scale as a low L state. So a trick to circumvent this has already been kind of demonstrated a long time ago by the CATMIN group, is to place this atom inside a plate capacitor. This, when you kind of tune the dimensionality of this plate capacitor, you can kind of use the Purcell effect and suppress the detrimental microwave radiation from the blackbody field. This is what we are trying to do in this experiment, and by that reaching long lifetimes in a room temperature setup. And I should mention that there's also work going on in rubidium that has recently demonstrated this effect. I'm not sure if these data have been shown on Tuesday, but they are all very beautiful and show that this works. So that is how the machine looks like on a drawing. We are using a UHV glass cell that allows us to have high numerical aperture optical access to make these tweezer arrays inside that vacuum system. And then inside that cell, we have designed an electric field control setup that consists, first of all, of this plate capacitor. And this plate capacitor is actually made from glass that is covered with a thin ITO film. So ITO is a material that is electrically conductive, but is optically transparent. So basically, make a capacitor where you can look through to get in your tweezer array, and at the same time, these plates have a high reflectivity for microwave radiation, and kind of form such a suppression capacitor to shield the Rydberg states from this detrimental blackbody radiation. And then around these two plates, we have designed electrodes that allow us to control the electric field very well. There is an ion detector in the vacuum setup that allows us to do field ionization and ion detection combined with this tweezer array. So we did a bit of work to actually think about these plate capacitor, because when we started setting up this project, I was a bit surprised that there's not much in the literature about how ITO films actually reflect microwave. So we did some work on this together with a group in Stuttgart around Dressel and Mark Scheffler, and studied how well do these ITO films actually reflect in the microwave domain, and how thick do you have to make the film to get a good capacitor. And for this, one has to know that the main transitions that would bring you out of the circular state with the strongest dipole moment are actually the ones that are connected via circularly polarized microwave photons to the next higher and lower manifold of the circular state, and they are typically in the tens of gigahertz to maybe 50 gigahertz range. And so we have done microwave spectroscopy, if you wish, of indium tin oxide films of various thicknesses in this frequency range, and discovered that you can get quite decent capacitor that has a reflectivity beyond 95% for the relevant frequencies with an indium tin oxide film that is about 200 nanometer thick. And so then knowing how to make these coatings, we have started setting up the experiment. Before I come to that slide, let me briefly show you the calculation, what you would expect then in this capacitor to achieve in terms of lifetime. So this is a plot that shows now the lifetime, the expected lifetime as a function of quantum number at room temperature in free space, that are the gray dots here. And then if you place this atom inside this capacitor with these reflectivity coefficients that you can reach the millisecond to tens of millisecond range, and that's what we want to do. We have then set up the machine, and we have chosen strontium atoms to work with. And the reason why I like that atom is that once you bring the electron to a circular orbit, you have the second valence electron left to play with. And so this optically active core is specifically interesting in the case where you have the circular Rydberg electron, because then you have an exponentially suppressed autoionization rate. So you can really start playing with this inner electron in a way as if you have a strontium ion inside your Rydberg orbit that you can use for all kinds of things. For example, you can kind of use the, let's say, the D line in strontium plus for trapping your circular state in the tweezer. So the rubidium atoms are typically, rubidium Rydberg states are typically anti-trapped in the tweezer. So here you have the polarizability of this inner core that can be used for trapping. You could think of doing collecting fluorescence of this on this strontium plus transition and have a way to directly detect optically the Rydberg state once you're in the circular orbit. And then on top you have a clock transition in this strontium plus core and a long-lived D state. And so this you could use to manipulate the circular state by optical means, or read out the circular state by optical means by playing with this inner electron. And there has been recently a very beautiful experiment in the Paris group on that, on a beam, on a strontium beam that demonstrated this. So that is now the first kind of line of single atoms that we have prepared in this experiment. Each dot here is fluorescence collected from a single strontium atom. It's 10 in a line. And I would like to discuss a little bit how we prepared this array, because we are working at a wavelength, the tweezer wavelength. We have picked the wavelength that is 240 nanometers. So first of all, for the circular states, it's an interesting wavelength range, because this you need to actually really use this trapping effect and keep the circular state trapped in the tweezer. But it is also a wavelength that is magic for a new qubit that we aim to actually also study in Stuttgart. So it's strontium, to remind you, what you have is singlet states and triplet states and clock transitions between the singlet S and the triplet P. And so this triplet P level here has a fine structure. It has three fine structure states at J equals 2, 1, and 0. And this tweezer wavelength here is magic for a Raman transition between the triplet P2 state and the triplet P0 state. Yeah? So in this state, these two states here, we actually want to use as a qubit. That has so far not been studied a lot, and we believe that it has some benefits that we would like to explore actually in a different setup, in a second strontium experiment that we are building. But now the problem that comes with selecting this transition is that if you have this qubit here being magic, then this narrow intercombination line here is completely off magic conditions. And this is typically used in strontium tweezer arrays to do narrow line laser cooling and bring the atoms to the motional ground state in the tweezer. So we had to think about how to do narrow line cooling in a completely in a way where the narrow transition is very strongly state dependent and not at all magic. So just to remind you, if you do, for example, standard sideband cooling, then what you have is that you have kind of a narrow optical transition where and a tight confinement to be nicely in the Lambda regime. And then you exploit the fact that your vibrational ladder in the ground state of your laser cooling transition equals the vibrational ladder in the excited state. And so this has been kind of exploited in many of the strontium experiments, including the seminal work by Manuel Entos's group and Adam Kaufman's group. So this polarizability ratio here between these two states that take place in the cooling, however, at our wavelengths is really strongly different to 1. Yeah? So this is the difference in the polarizability between ground and excited state on this cooling transition as a function of wavelengths for 2 different Zeeman states. And here we are working, and you see it's a really, there's a very strong difference in the trapping. Specifically, in our case, the ground state is much stronger trapped than the excited state of this transition. And for this reason, if you let's think about now, you want to implement some sideband cooling, then what actually happens is, if you're on the red sideband transition to cool the atoms to the motional ground state for low-lying vibrational states, yeah, then if you climb up that ladder, then this red sideband condition will actually turn into a blue sideband condition. Yeah? And so once you try to cool atoms that are already deep in the trap, you will heat out atoms that are in high vibrational states. Yeah? So that means with a single frequency that you would shine in, you would not be able to bring the atoms down to the ground state like you have it in a magic trap. And so what we have tried to do is to do that cooling and the sideband cooling in a way that you have a laser frequency of this narrow transition that you chirp to kind of go through all these sideband resonances one by one and really bring the atoms down from highly excited levels down to the ground state. And because you're in this very non-magic trap, this actually also works a bit different than you're maybe used to it in the standard sideband cooling regime, where you typically don't have direct coupling between oscillator states of the same parity, but here you can have it because the states in the upper electronic stages look very different. So there's a direct coupling, and that kind of influences the cooling dynamics. For example, you can really use the fact that you can drive transitions between states that have, for example, between state 4 and state 2 in a direct way, and that kind of speeds up the cooling rate in the system. So we have implemented this. We have worked on one of these 2 resonances of the 2 Zeeman states and implemented this frequency chirp, and then have studied the temperature of a single atom in such a tweezer as a function of the frequency detuning from the trap shifted resonance, where you kind of stop this chirp cooling process. And this is a plot that shows a release and recapture measurement, where you kind of open the trap, you let the atom fly out, you close again, and you kind of measure the success rate of retrapping the atom. And so the colder you are, the longer you can kind of release the atom and recapture it. And you can nicely see that this cooling works very well. And the lowest temperature you reach when you actually get when you end this chirp roughly at the red sideband condition of the lowest vibrational state. And from these, one can compare now these release and recapture measurement to kind of Monte Carlo particle trajectory simulations to check how good one is in the harmonic oscillator ground state of this tweezer, and it actually works quite well. To be a bit more quantitative, we have measured this in 2 different resonances as a function of the final detuning, and then you can actually compare the minimal temperature you can achieve to the 0-point motion, the radial 0-point motion in the trap. And from that, we deduced that we have a ground state fraction of about 80% using this technique. One can go one step further to characterize this and actually do sideband thermometry on the less shifted, still a non-magic resonance, yeah, but it's a bit less shifted, so you can resolve the sidebands once you're cold enough. And then you can study sidebands by doing spectroscopy on a single atom as a function of temperature. So this is a data set that is taken at a slightly higher temperature. The blue one is a data set that is taken at the lowest temperature we could reach. And you can clearly see how this is the blue sideband. Here's the red sideband. You cannot even see it. So you can nicely get a asymmetry in the sidebands, which signifies that you're very, very well in the ground state. And also from this data, we can estimate or we can get a quantitative measure of the ground state fraction that is in these recapture measurements. So I found that a nice technique because it applies now to systems that you cannot magically track. And so I would be interested to discuss what else one could think of. Maybe it would be interesting for molecules or so, where you don't have magic conditions, and try to bring the atoms down to the ground state. The second thing that you would typically need when you have these tweezer arrays is parity projection to have really single atoms in the trap and then resorting them. And this cooling technique actually brings you this parity projection essentially for free. And so the first reason is that if you cool down, then the density in the trap becomes larger and larger. So the light-assisted collision rate actually goes up and reaches very high rates. But at the same time, strontium has the favorable condition that the last bound state of the was 1s0 triplet P1 asymptote is actually just about 400 kilohertz trapped. So when you do that frequency chirp, you always hit this. So at some point you couple two molecules in the system, and one can nicely see that. So this is a histogram of the photon counts for a single atom. This would be no atom in the trap. This would be one atom in the trap. And when you don't do cooling, you have multiples, 3, 4 atoms, stochastically loaded. But when you then apply this cooling chirp, you get a nice bimodal distribution and, so to say, kick out all the higher occupation numbers. And one can study this as a function of this final detuning of this frequency chirp of the cooling ramp, and nicely see how these multiplets actually go down. These multiples go down and only the singles survive, and you end up with a probability to have a single atom in the trap that is at the end of the ramp around 50%, and that's a nice starting point for doing rearrangement. Okay, that was a bit technical, but I wanted to share this, and I will actually put this in a paper that will recently appear in FirstRef Research. And now let me, how much time do I have left? I have 5 minutes. Okay, let me talk a little bit now about the more recent stuff that we did now on the Rydberg. So we have now atoms in the tweezer, and we could start to excite them now to Rydberg states. So to explore the path towards Strontium Rydberg as circular Rydberg states, the first thing that we want to do is we want to actually get them to a low L state that would then be the starting point for the circularization. And we're following 3-photon excitation down from the ground state all the way up the singlet branch via the 1p1 state, the 1d2 state, and then finally coupling 3 photons to singlet F Rydberg states. From this F state, which is, it has in strontium, it has quite a large quantum defect compared to rubidium, but it's sufficiently close to the hydrogenic manifold that you can think about starting then the transfer from this F state to the circular state using the radio frequency adiabatic passage technique that has been pioneered by famous people in the past. And so this is our first data set where we have excited to this Rydberg state here, to the, in this case, 70 F state. That was the first crucial partner that we can check if our field control works, and if we can control the electric fields to a good degree of freedom. So that was one of the first Stark maps that we took for this F state in our setup, and then we wanted to explore the limits of this field control, and we went higher and higher and higher in N, and that was kind of where we stopped. That is now a Rydberg state in the setup that has a principal quantum number of 212. It's a P state, so we changed to the P state that has a bit smaller polarizability and makes it a bit easier. But if you look at the scale now here, you see that, I mean, this Stark map here of this P state is controlled at a level of a few millivolt per centimeter, and you get shifts on the order of megahertz. And we can do that in 3D. So the electrodes are made in a way that you can do that Stark map in 3D and kind of compensate the field in all 3 directions. And then we checked for like how stable this electric field is that we can control on a level that is better than a millivolt per centimeter. And we found that really, I mean, if you you can switch off the experiment and come back 3 days later, and the field is still there on the order of a millivolt per centimeter. So it's really extremely low drift rates, and we are very happy with this. And that actually allows us now to control the very high-end Rydberg states in a tweezer array. I mean, in Stuttgart, we have played a lot with electric field controls and over many years, and but never with single atoms and tweezers. So now you can actually make Rydberg atoms in a tweezer array that has a diameter of 8 micrometers. And I find that a kind of interesting perspective, because now there's Matt. Is it on already? Ah, he's still there. Yeah. So a couple of years ago, he has thought about Rydberg molecules where you have control over the position of the perturbers. And at that time, I think everyone you've been talking to said, "Oh, this is crazy stuff. Who should measure this?" But now can think of a situation where you have a single Rydberg atom in the middle, and then you position your neutral atoms around that Rydberg atom, because this you can do now. So the Rydberg orbit is now, I mean, reaching into the next tweezers, and you could think of situations where you place neutral atoms around your Rydberg and try to measure these situations where you get these trilobite wave functions on multiple perturbers with controlled positioning of the perturbers in the Rydberg orbit. So I find that a very cool perspective. Okay, that is I think almost my last slide, almost. So from that on, we have then tried to couple now this Rydberg F state to the circular Rydberg states, and this is really very fresh data just from last week. We see some kind of signature that indicates that we can bring the atoms towards the circular state. We have implemented a radio frequency adiabatic passage. These are the parameters at around 50 megahertz coupling between the individual Stark states, and then we ramp the electric field through this resonance condition to actually try to adiabatically drive the F state to the circular state. And the first thing one typically looks for is the field ionization signal in a state selective field ionization measurement, because the circular state will actually tend to ionize at about twice the electric field compared to the low L states. And so this is the field ionization signal for the F state. And then we apply this passage, and what we get after the radio frequency is applied is a signal that is, this is a arrival time in the detector. So it's really fresh data, but if you would convert that into an ionization field, then this is very well at the position where you would expect the ionization of the circular state. Now, the next thing to do is to actually check how well we end up in the circular state, because the ones that are close by the elliptical states with 1 m less tend to actually ionize the same field as well. So just this field ionization is not enough. We have to now probe this circular state using microwave spectroscopy, and this is what we are now implementing. And then we can actually check the state purity and optimize it. Okay, with this, I'm actually at the end of summarizing what is going on this new project, and I think the fun stuff starts now. I'm really looking forward to the next months to play with these high L Rydberg atoms. Apart from that, I would like to mention that we are also setting up a quantum computer demonstrator experiment using strontium atoms that tries to implement this new fine structure qubit that I was mentioning a few slides ahead. And so this is all happening around Tillman. It's a consortium where Tillman's group, myself, Hans-Peter Büchler is involved, Simone Montangero from the University of Ulm takes part, and Toptica is an industry partner, and then several subcontractors that we are working with. And this is an experiment that is really in the build-up phase. So we have a mod now, a strontium mod on this setup. but no atoms in tweezers yet. So we are working towards that. Nevertheless, the idea of this project is that such a computer, as we all are aware of, should finally be used by someone. So what we have been working on is to provide an interface. That is mainly what Hans Peter's group is also doing there. That should allow external users at some point to use that machine. So far there is no machine, yeah, but the interface is there. So we have actually set up a website that already allows you to play with an emulator that should finally be replaced by an access to the true quantum computer. Yeah. And together with this emulator, we have also set up a quantum circuit designer that has a nice graphical user interface. And that actually comes along with a very nice tutorial, which I would highly recommend to maybe check out this afternoon or so, because this has been written by people from Hans Peter's group, and it's really made in a way that you can use this for educational purposes. So you don't have to know anything about quantum mechanics. And by reading through this, you can try to make your first circuits and try to understand what entanglement is. And so it's I think it's a fantastic educational piece that can all be found on our website. And so with this, I'm really at the end. I haven't put the full team. This is only the team working now on the circular atom experiments. And I would specifically highlight Christian Hölzl here, who was the PhD student that built this setup together with me from scratch. And with this, I'm at the end. And thank you very much for your attention.
Question about the inhibition of the black body transition. So when we trap our molecules around, we often see at room temperature effects of black body photoionization. And so I see that in this small mode structure, you'll inhibit the transitions between nearby end states. But have you looked at the effects of photoionization? This could also be enhanced maybe by this cavity effect.
No, I have not. But so I have to put the numbers, because in our case, this capacitor is rather large. So we have roughly a centimeter. And the reason is we try to make these circular atoms at high end. That is the goal. But then what are really the rates for photoionization? I'm not quite.
We often see rates of a few kilohertz.
Okay.
When we put a heat shield around, it gets a bit worse, and then we cool, and then it's sort of away.
Okay. That would be interesting.
Yes. When we started with the height mountains, it's very sort of first, but we see it in all of it.
Okay. But we should something like that. That's pretty great. Yeah.
Bit of a technical question, but so you showed that you have this paper called something. What was this? Presumably you have to apply some compensation to achieve that field?
Yeah, the typical stray fields that we compensate are on the order of 10 millivolt per centimeter.
What challenges will apply includes electrode voltages?
So actually, I think what we are really limited here currently is electric field noise on the plates that comes from the voltage source. And I mean, one could do a lot in filtering, but what we need is this. I mean, we also need to have some temporal control, because we need to change electric fields for the circularization procedure. And so we use an AWG from Zurich Instruments. It's Hardy HD AWG, which has quite low voltage noise on the order of it's below 500 microvolt level, peak to peak, and I think this is exactly what limits us now. So.
Yeah, and then you mentioned that there's in fact a puberty according to the 50 and 52. So what's the advantage?
So yeah, okay. So there's multiple things that are advantages. So the first thing is you can connect these with a Raman scheme And that allows you to make very fast single qubit gates on the order of 100 nanoseconds. And so if you compare that to the clock qubit in Strontium, it's a much faster qubit. Yeah? But it comes with challenges in terms of coherence time, because this triplet P2 state it has a tensor light shift. Yeah? And so you have to control the polarization of your tweezer very well, otherwise you would get dephasing. So it comes with a shorter coherence time. We want to achieve tens of milliseconds, yeah, so but much faster gate times compared to the clock qubit. So this ratio between gate time and coherence time is then comparable. Yeah? But the whole computation can be done much faster. And then the second thing is that for this qubit, you can actually find, and that's why we are working at this 540 nanometer, you can find a magic trapping condition that is magic for the qubit, but also for the Rydberg state. So you have all the three states that you need for your quantum computer, the qubit and the Rydberg state, trapped in the same potential, and that is good for dephasing the Rydberg gate.
So when we compensate the field to below 1 millivolt over 3 dimensions, we find that the remaining source is actually the applied potential to compensate that are not homogeneous. So I guess this must also have, or
yeah, I mean, sure, there is some, you mean over the array now, yeah? Yeah, so we have not measured this. I mean, in the simulation, I mean, we have put the SimIn and checked it, and it looks like that this inhomogeneity of the field is probably on the same order than this millivolt per centimeter level on the 100 micron scale. Yeah. Yeah.
Any more questions? There might be one on chat, maybe Michelle or someone.
Yeah.
Let's see.
Wrong mouse. Okay. Thanks a lot. Okay.
So if there are no further questions, join me in thanking Florian and all of the speakers. Many of you have travel plans, and anyone who can go as soon as possible. I heard that the region also many strike and so I'll be short. No conference is possible without the active participation of the scientific source of the people who come to the knowledge. Thank you. And I think all of you have made, which I think has been a very successful conference. But the conference is never successful if there is not an effective, efficient host who can attend, who's attentive, and also who are attentive and are available to respond to all of the challenges which require to put together the conference in a complex environment like here. So join me in thanking Stephen and this group, his team members who were here and are still here. In putting together this beautiful meeting. Thank you. Two years time, I think most of us, or some of us, or all of us perhaps, will be in Granada, where we will have the largest challenge we will have finding is the flat surface to place software. But bring your cats, because in 2025 is a very special year in business. I'm not sure. Say yours.
It's amazing how it's so we can do some